Get started, so we ought to get started here, and I will start, like always, with kind of a description of where we are and where we're headed. I'll say it again, I think you know this class is divided into kind of 4 mini classes, starting with the wave motion that we've kind of been plowing through real fast, and we're ready to call it quits to that, except for we have the exam to take. And so the next time we get together, which is Tuesday, and so you've got 2 holidays here. Tomorrow is one of the President's Day, and Monday's the bigger holiday, President's Day, the one where most people get off, not just schools. But Sunday is designed to be a review session for you. So at 1 o'clock in here on Sunday, again, Don from the MC class will come in here and give you a little review. And I know some of you have already been talking with them and getting their little review sheet and all that good stuff. So anyways, I'd encourage you to make plans on Sunday to be here, and then I will see you on Tuesday, 8 in the morning, and we'll throw it out there. 2.5 questions, give you an hour, and we'll kind of collect it, and then we'll go on more with our thermodynamics. Question?
Do you know if Don will be here on Friday?
Yeah, I think he's, I don't think he'll be here on Friday. And of course that is chapters 15, 16, 17, and 18. As mentioned, we've been rushing through, and so now we're going to give you a week for that to sink in. And I say a week from Tuesday. Now I guess it's only 4 days. No, 5. I can't count. 5 days from today is your test. So you got 5 more days for that to sink in, and I trust you've been working on the homework. Meanwhile, though, we are going to move forward here and go into our next unit, which, if you recall me saying, is our thermodynamics. And so let's take this day, this opportunity, to kind of set the stage for our thermodynamics. And again, just like we did with our mechanical waves for the last 4 chapters, we are going to do 4 chapters on thermodynamics. So 19, 20, 21, and 22. That's that homework package that I just sent around, which I only had a few. I didn't even dawn on me to make more. But we will. And Don actually said he's going to go over to the copy center and make some more. So if you're dying to get your hands on it before today's over, he will have them before class is over, and then later in the day we'll have obviously a lot more. And so when you are in lab, or if you already did lab, come by and you can get more, or you can just wait till Tuesday and get some more there, because my hope is to talk about the fundamentals of this chapter, which is probably most of the chapter, and most of it you've seen before, maybe not quite in the light that we're going to show you now, but all of this, I think, is a review, and that's why I think the lecture works out well, in the sense that let's get started with our thermodynamics. Let's do, the way Don describes it, the lightweight stuff, and let's get that going, and then so after the test we can get into some of the heavier stuff. But I think you'll see all this, and if you've had a chance to look at 19, you've probably already noticed that. In fact, I would probably say all this in 19 and the first half of 20 you've seen, and then we would get into some new stuff that you haven't seen. So the best way for me to get started here is to put that on the board here, is that here is our new unit, if you will. It's the chapters 19 through 22. It fits into this category of what we refer to as our thermal dynamics. And so what is going on in terms of heat and temperature and pressure. And so if I was kind of given a simple, quick definition of thermodynamics, I would say, okay, what is thermodynamics? Well, this is kind of our discussion of energy and the transfer of energy. So it's the relationship between heat, temperature, pressures, densities, maybe I'll just stop there, etc., etc., etc. We have our laws of thermodynamics. And so just like we had our mechanics, and we can go back and say, give me any kind of motion and I can apply Newton's 3 laws of motion and explain that motion, which also those go with our conservational principles. Same thing here. We have our thermodynamics laws. I'll say our 3 laws of thermodynamics, although as you are going to see after the 3 laws were kind of written, somebody stepped back and said, you know, make this a little more formal. This, which is so obvious, should also be kind of put in there as a law. And so it doesn't deserve a number 4, it deserves a number 0, if you will. So we have our 0 through 3 laws of thermodynamics, and so we will be discussing those. And this chapter, in a few seconds here, we will mention the 0 law of thermodynamics. And you'll see it's kind of more of a formality and a kind of an obvious situation, but it's good to have that formality so that we can refer back to it. And in fact, you'll notice as we study our thermodynamics, we can study it on what I would call a first level or an easy level, surface level, if you will. Or we could go a little bit deeper. We could get down to what I will call the microscopic level. And so maybe I should put this first level is probably what most of you have seen before. The microscopic, probably have seen that to some degree also. But as we look at our thermodynamics, it's nice to look both at the big object and at the little object. And so when we look at something like this, we can either ignore that it is made out of many, many, many tiny pieces of, this happens to be aluminum, so aluminum atoms, or not. If we kind of ignore it, we just see it as one continuous object. That's kind of a macroscopic view. If we dive a little bit deeper, we see that, okay, down deep inside, this is made out of billions and billions and billions of aluminum atoms. And so what's going on a microscopic level? Maybe a little formality here is to say, let's call this then the kinetic theory. Meaning that, as you'll see as we go through here, the development of the kinetic theory. And the kinetic theory is that everything is made out of the atoms, and these atoms jiggle around here. If you warm it up, they jiggle a little bit faster. If you cool them down, they jiggle a little bit slower. And so those are going to be our 2 perspectives. And I'm going to do something a little different than the author. Most of the time I always say I like to do exactly what the author does. Even sometimes when I don't think it's maybe the best approach, it's usually a good approach, maybe not best approach. And for me to deviate from that, I always say, well, that's going to confuse the students and make things worse. So I try to be in parallel there with the book. But one thing I really don't like about the book here, I shouldn't say don't like, but I think he could do a lot better here, is if he would start the microscopic view right here at the beginning. He doesn't really get down to the microscopic view till 2 chapters into thermodynamics. And so he avoids this whole idea that everything is made out of little tiny atoms and they're jiggling around. He focuses, I think, too much on the macroscopic for too long. And so I'm going to just start talking about microscopic already. And so by the time we get to chapter 21 and he starts talking about the microscopic level, we're going to be halfway done with chapter 21. We're going to say, okay, I get that picture. I get that idea. And so here's what I mean by this. If you kind of have this mental picture here and say, all right, if I could look really, really small, what would this look like? And if those represent the aluminum atoms, they're kind of bouncing around. What would happen if I heated it up? They'll move faster. And so we'll have a lot of discussion about the molecules moving around that, like I said, he doesn't spend too much time in these beginning chapters on that. In fact, let me start the chapter in that way. Here's where he starts. He starts with a lot of vocabulary and throws out some words. He starts with this idea. What if you were to take an object that is hot? All right, so that's why I brought these little blocks out. So imagine that being a hot piece of aluminum. And then you put it next to a cold piece. All right, well, let me take a piece of brass and put them together. And so I touch them. You probably already know what's going to happen. Yeah, what's going to happen is this hot object is going to lose something. It loses what? Okay, I would say it loses some energy, or what the early scientists said is heat. They didn't know heat was a form of energy. They didn't really know what it was. It was kind of this first level approach, kind of like a liquid. You would have maybe this side has some water, if you will, and you lose some water, and so the water goes from one object to another. And so without really knowing what the heat is, knowing that it's an energy, and certainly not knowing the more microscopic level that it's the movement of molecules, we can just say there is a movement from one side to another. Something moves. And so heat, then, our first word for the day and for the chapter and for whole thermodynamics, is it is the amount of energy that is exchanged. How much energy was exchanged between these two objects? And like I said, the early scientists just called it heat. They didn't even know it was an energy. Later on, they figured out it was an energy. And then finally, later on, we even get down to the microscopic level. And so I'll start with the microscopic level. What would you say about the molecules that are in this hot object? Yeah, they're moving faster. And so what happens when they come in contact with those molecules that are in the slow object? I mean, the cold one, which it means they're slow, right? And so when you put fast-moving objects next to slow ones, they collide, and the fast ones slow down, and the cold ones or the slow ones speed up. Exactly. And so that is what is happening on a microscopic level. And I think it helps, actually, and this is what I'm getting at, to mention that on a microscopic level. And your author won't do that quite yet. He's going to wait a couple chapters. But it's good to have that microscopic view here. And so again, first word, heat. What is heat? Well, it's the exchange of energy between them. Which brings me up then to the units. What unit should we measure this new word and this new idea as we get started with our thermodynamics? Okay, joules, good. It is a form of energy. And again, I think the microscopic level does help here. Of course it is. It is a kinetic energy. You might call it an internal kinetic energy versus a bulk kinetic energy. But when we were in Physics 121 and we said like the car has kinetic energy, what we really meant is all the molecules were moving in the same direction. That's why the whole bulk material moved from one point to another point. Now, we are saying that they have more of a random kinetic energy. And this car does not move from point A to point B, but some of the molecules, about half of them, are going to the left. At any moment, the other half are going to the right. They kind of stretch back and forth like the springs we had in chapter 15. And the energy is there in a form of kinetic and potential oscillations, but it's just kind of this random collision, and so the whole object doesn't move. And so again, I think it does really help to mention the words and understand the macroscopic level, but also take it a step deeper right here at the beginning and go to the microscopic level and say this is what's going on. These molecules are moving. So it is measured, not a surprise, in joules, the same units that you used to measure the kinetic energy of a car or the potential energy. But that's not the only units. Little history is in order here. Remember I mentioned that, again, the early scientists thought of this as maybe more of a liquid. Like, hey, something is moving. We don't know what it is. We'll call it heat. It wasn't until later on they realized the heat was a form of energy. And it wasn't later on until they realized that that was the collision of these microscopic things called atoms and molecules. But they were already measuring heat, and they'd already given units to it. And so another unit that we will measure heat in is, again, probably one you've seen before. It is a called a calorie. And so maybe it'd be worth starting this chapter on reminding you, I'm going with the idea that most of this is a review here today, of the definition of a calorie. Do you guys remember what definition from a calorie is? I know we did it in 102. Yeah. Good. The amount of energy needed to what? Heat or raise water 1 degree Celsius. Oh, maybe I should say 1 gram. To raise 1 gram of water 1 degree. Okay? And so, again, you can see kind of the early scientists' idea. They would start off and they would say, okay, let's do this. Let's take 1 gram of water here and put a flame underneath it. And that flame then would make heat that would flow into the water. Again, not knowing its energy, you're saying, okay, it's flowing. There is a movement of something from this candle to the water. And when that 1 gram warms up 1 degree, it had transferred the equivalent of 1 calorie, whatever that meant. Fortunately for us, Joule did realize that these calories then, this thing called heat, is a form of energy, and he did a very classic experiment by measuring it. He took a weight, an actual mechanical weight, and he took this large mass and he put it in the top of his laboratory, and on that he made a pulley system. And that pulley system then came down to a beaker filled with water, and I don't have a good setup for this, but he had a little paddle wheel in there. And he said, okay, when that paddle wheel goes around and stirs up the water, that's going to warm up the water. So he releases the weight using gravitational potential energy, knowing how many joules that is. And then he uses a thermometer to see how much the water raised in temperature, and gets a clear connection between the energy measured in joules from the dropping weight and the energy measured in calories from the warming of the water. And so one of the first steps here was to find out that relationship. And so today we know that there is 4.18 joules equaling 1 calorie. And so you're going to see that as we go through our thermodynamic unit. Sometimes we will measure our heat energy in calories, and sometimes we will measure them in joules.
So it's a little c though, right?
Oh, and good point. This is a little c. There is also a capital C calories. Those are the ones that are used in nutrition labels, so don't confuse the calories that you'll see, on a menu at the restaurant there saying how many calories is this. Those are referring to the capital C. What is the capital C? Yeah, we in a science class will call this a kilocalorie. It represents 1,000 of those. And you can see why it becomes useful in terms of nutrition, because it would be a way of saying how much energy is needed to raise 1 kilogram of water 1 degree. And so the capital C is a description of 1,000 times more energy. But in a science class, we don't usually see the capital C. But it's always fun to, compare. And I remember the 102 class, and I think you have one very similar to this. It says a piece of cake is 400 calories with a capital C. How many joules is this? And so we've got some unit conversions to do.
Most of our calories spent for our body temperature?
Oh, yeah. So, and it's also why then you begin to realize that this unit of calorie is really a unit of energy. It's energy consumption. And your body then, when it eats calories, is taking in energy. That's what you are measuring. How much energy is stored in the bonds of all those chemicals. And if you take in a lot of calories but don't do a lot of exercise, obviously you have then brought in more energy than you have used. And so that energy is then stored, little fat cells here, waiting for the day that you will do more exercise than calories you take in. And so then it has some place to go to get that extra energy it needs for that day. I'm still waiting for my day where I do more exercise than I eat, but it's that's the way human or all animals are made. I think bears are probably one of the extreme cases, right? They forage all spring and summer and eat lots and lots of food, bring in lots and lots of calories, far more than the exercise they do, and they just get bigger and bigger and bigger, only then to go hibernate all winter long, and then 4 months without eating. Hard to imagine, but 4 months without eating. But and then they just live off the energy that's stored in their body fat. All right. But again, all of this I think you have seen in one way or another. Again, let's keep going just to get these words straight. For example, if you understood this word heat, see if this question makes any sense to you. I had purposely put out here a large beaker with lots of water in it and a small beaker with just a little bit of water. Which one has more heat? Do they have the same because they've been sitting in the room here? And then I would assume they're kind of at the same temperature? Or does this one have more because it has more molecules than that one? Or is it just an inappropriate question because heat is not how much do you have, but how much moved? How much moved? None. That's a silly question to even ask which one has more heat. If one was hot and one was cold and I put them together, I could say, how much heat did this one lose? How much heat did this one gain? That's an appropriate question, not which one has more heat. And so I ask it that way to make sure you don't confuse what we are going to see as three important ideas that are so easy to confuse, and that is heat, thermal energy, and temperature. And I'll say it again, heat is this amount that actually flows. It's not how much the object actually has. It's like having $100 in your wallet, and then as you spend $3 on a coffee, the $3 is how much is transferred from your wallet. That's like the heat, how much actually moves out of your wallet, not how much is in your wallet. You could have had $100, you could have had $20, you could have had only $3, but the heat that transfers out of your wallet, the money that transfers out is $3. That's the heat. The thermal energy then is really the question I was asking, which is the total amount of energy. And so really a question that I should have asked you was not which one has more heat, which one has more thermal energy. And you still might not know the answer to that, but you say the big one and I'll say yes. And why the big one? Just because there's more molecules here, right? See, because I would say that because they've been sitting in the room for the last hour here, they have the same temperature. And what I mean by that, temperature is how much energy does one particular atom or molecule have on average. And so when we say something is at the same temperature, here's what we mean. If you go down to this microscopic view, you are saying that on average they have the same. And the reason I put average is because remember, what is happening on a microscopic scale is this atom is here and it's bouncing around. if I turn this back on for a second, and if you kind of look at one of those little ball bearings in there, sometimes it's going fast and sometimes it's going slow. All of them are that way. But if I were to look at all of them at one instant and or look at them over a long period of time, don't they have an average? And they probably have the same average over a long period of time as they ricochet around. So I would say then that all the molecules have some kind of average energy. At any moment, they may have more than an average or less than an average, but at some long period of time, if I were to measure their energy over like 1 second and see that it's been hit, and real molecules hit about 100 trillion times every second. Sometimes they're going faster and sometimes they're going slower, but they will have an average. And what I'm trying to say is, as I look at the big beaker and the little beaker, they're at the same temperature. And their average energy of a molecule in here and the average energy of a molecule in there are the same. And so when I ask what is their temperatures, oh, they're the same. But one has more water than the other. So if I ask the other question, what about their thermal energy? Do they have the same thermal energy? No. Which one has more thermal energy? Yeah, the big one. Not because the molecule individually have more energy, but because there's just more of them, more molecules. And that's the important distinction between these three words and our first words for the day. What is heat? What is thermal energy? And what is temperature? And so, like I said, that's where your author starts. He does those three. And then he does two more words here to get us started so that we can have our zero law of thermodynamics. So after heat and thermal energy and temperature, he says, well, what about this word, thermal contact? Well, thermal contact is really what I was trying to convey here. If they are in thermal contact, that means the heat can flow between them. There can be an exchange between them. And so if there was something in between them, like a big piece of styrofoam, which we're going to call is something that is a thermal insulator, it won't allow, say, the motion of the fast ones to come in contact with the motion with the slow ones. In fact, if I had nothing more than to put a gap between the hot one and the cold one, like that. Of course, there's actually some air molecules between them. Air molecules kind of move the heat from one to another. But let's say there weren't any molecules in between them. Then I would argue these are not in thermal contact. They're not having the ability to transfer the heat from one to another. I got to get them close enough so that the fast-moving ones can then collide with the slow-moving ones. And that's this whole idea of thermal contact. So we need to pay close attention as we do our thermal dynamics. Are the objects in thermal contact? Can heat flow? Or can energy flow? Can there be a heat exchanged between the two? Sometimes the answer is yes. Sometimes the answer is no. Sometimes we will want it. Sometimes we won't want it. But once we put them in thermal contact, then the energy flows, which we're using the word heat for that. They will flow not indefinitely, but until we get to what we're going to call an equilibrium, like we did with the pendulum, like we did in chapter 15 with the mass on the spring. If you put a mass on the end of the spring, if you were to pull it too far down, what you meant by that is you've stretched the spring more than the force of gravity. So when you let it go, the spring wins and goes back up. If you lift the weight up, well, then the force from the spring is not as much as gravity. Gravity's winning, if you will, and it goes back down. But there is a balance point, an equilibrium point, and if you put it there, it stays there. There's no exchange going on.
If the objects aren't touching, is there also not photons exchanging?
Well, yeah, I didn't necessarily want to, this is next chapter, but there are many ways that energy can be transported from one to another. And I gave you the simplest one where one molecule is moving, colliding into another. We call that conduction. I separated them and said there was no thermal contact. What I should have been more accurate with, say there's no conduction. There is, as you're pointing out, photons or radiation. And so there is a transfer of energy through radiation. Like I also said, there's really air molecules there, so I'd say there's a little conduction. And if the air molecules are flowing in any way, that would be our third possibility, there would be some convection. So there's never really a situation where you could have no thermal contact. It's just how really well is the thermal contact. So two metals, the thermal contact is great. Put a little air between them, and the rate at which it transfers energy is really, really slow. Not zero, but it can do it by radiation. But that's pretty slow, at least at room temperatures. You start to get things really warm, and then the radiation you can feel. You probably stood in front of a fire and felt the warmth. That is warming you a lot by radiation. But that's because of a different temperature range than room temperature. Yeah. So, yeah. But then going back to this thermal equilibrium, this then is where we've been maybe exchanging energy. That heat's been flowing from one to another for a moment. And eventually, it stops. There is no more flow of heat. Then I will say no net flow of energy. Because here too is a good chance to kind of pause and look at the microscopic level a little bit more than your author does here at the beginning. But when two things stop exchanging heats, what's going on? Why do they do that? So again, if these were in contact and these were going fast and these were going slow, what will happen is the fast moving ones collide with the slower ones. The slower ones speed up and the faster ones slow down. And then eventually they get about the same speed. What happens there? Yeah, then there is no net flow of energy. And what I mean by that, at any given moment, as these things collide around, there is a chance that this one over here, which originally I called it a cold object, that molecule actually goes really fast. And there's a chance the one right next to it is now going really slow. So what would happen there is after this one went fast for a moment and that one slow, that one would collide in there, and then this one would lose energy and that one would gain energy. In that case, I would say there is a movement of energy now from the cold one back to the hot one. But statistically, this is probably happening equally all along there. So there is still a movement of energy, if you will. There's no net movement of energy. They are statistically the same. And so then we say they are now in thermal equilibrium. Yeah.
What is moving again? What's moving?
Energy.
Not like any molecules?
Yeah, right. So again, and I don't know, maybe I'm making this too hard at the beginning by looking at the microscopic level, but if I take a dividing line and I'll put them back together here, there's a molecule here and a molecule there. The molecule itself does not move. So this one's going fast. Well, let me do the same order. This one's going fast and this one's going slow. And so as this fast one, and you put them together, hit, eventually this fast one slows down and this slow one speeds up. So what moved was energy, kinetic energy. this molecule is now going faster. This one is not. So material didn't move. The energy moved. And it's not really quite like a wave because it's not a uniform organized set of pattern of them.
I meant like wave,
But-
nothing actually moves.
Right. But like the wave ones we've been doing, you could have a movement of energy without the movement of the material itself. And that's what we have, at least in this form of heat, conduction. Because we also can have convections. And in that case, the molecules themselves actually move. Well, as I said, I just kind of wanted to start this first half hour with a little bit more than a half hour with kind of that formal idea. What are these 5 words here? And not to confuse them. And sort of give us a microscopic picture of these 5 words. And so that hopefully as we move forward, we can kind of get a physical mental picture as well as the mathematics, and that will help us, I think, tie things together, especially as we get to the more complex thermodynamics that will start to take place in a couple of weeks here. But that does start us off then with what we are going to then call the zero law of thermodynamics. One that, as I said, is hopefully relatively self-evident from what we set up here. And your author writes it this way. There's certainly different ways of writing it, but he says, if objects A and B are separately in, here's these fancy words here, thermal equilibrium with a third object C. Then, well, I'm going to stop right there. So this first part is saying, let's take 2 objects, A and B, separately. All right, so I'm back to these 2 beakers of water. I've got the big beaker and I got the small beaker. So let's call this A, let's call this B. They're not touching. They're not in thermal equilibrium. What this is saying is, if you have 2 objects, A and B, and they are separately in thermal equilibrium with a third object. All right, well, let's take this piece of aluminum for a moment. This will be object C, okay? And of course, what we meant by that word thermal equilibrium then is if I put these in thermal contact, so I touch them together like that, there'll be no flow of energy. There'll be no heat. But the same thing happens here. So what do you think would happen here? No flow of heat also. And so we say, then A and B are in thermal equilibrium with each other. Okay? Which, again, some of you are laughing like, well, that's silly. That's obvious. Okay, fair enough. And you can see why it was kind of just overlooked as the obvious, and first law, second law, third law, well, let's come back and put that. Because it does then lead to a formal definition of temperature. And that's really kind of the first measurement we're going to start our thermodynamics with, temperature. Because let me change object C from being just a piece of aluminum to being something else. Something else that changes when the speed of the molecules change. Well, I think many of you will recognize this. This, of course, is a thermometer. And that's where this is leading. This zero law of thermodynamics leads to the idea of what is temperature and then how do you measure temperature. But it's simply saying this. If I were to take this and put it in here, so again, object A, object C, and say these two are in thermal equilibrium. That means the molecules that are in this thermometer, which in this case it's made out of mercury, okay, they're going a certain speed. And I put them in here. The speed of those molecules makes the mercury go up the capillary tube. And so they're at some point. If I put it in here and say it is also in thermal contact or thermal equilibrium with B, then that would mean the molecules or the atoms of the mercury don't go any faster or any slower. And so what about the height of the mercury column? It is the same here, right? And so if I use this to define temperature, then I would say those two objects are in the same temperature. And so this third object becomes the measuring device to decide if two things are at the same temperature. They are really saying they are in thermal equilibrium when you bring them together. You may never ever bring them together. And so I don't have to ever put these two beakers together. If I don't put the beakers together, I wouldn't say they're in thermal equilibrium, but I would say they're at the same temperature. And that's what the zero law does for us. So the zero law gives us more of a formal way of defining what is temperature. And here's the two hopefully obvious pieces out of this in the first section of chapter 19 here. It says, two then objects in thermal equilibrium with each other are then at the same temperature. And so that's going to be our definition of same temperature. They're at the same temperature if they're each in thermal equilibrium with themselves. Or the same way, if two objects have, and this is going to be the important one, but again, something I think you probably already had a gut feeling for before you got here today. If two objects have different temperatures, exactly, they are not in thermal equilibrium. And so this idea of temperature is a way of measuring how close two objects are to thermal equilibrium. And so that opens up this new idea of what is temperature. And so temperature is going to be related to really thermal equilibrium. Two things at the same temperature, they're in thermal equilibrium. They won't exchange heat. They're not at the same temperature. There will be one that will send heat or energy from one to the other. That's really what the zero law is trying to say. And again, something that I think in your world you've already experienced so often that you kind of accepted that as given without the formal wording placed in there. And so, fair enough. And it does then lead us to really kind of the first major work in this chapter, other than vocabulary and the basic zero law of thermodynamics. It leads us to, well, how do we measure temperature? And again, before you came here today, I'm sure you knew the word thermometer. What is a thermometer? Well, it's a device used to measure this temperature, this idea of how close or far apart are two things in thermal equilibrium. Oh, there's a lot of ways we can build a thermometer. I've given you the very common, maybe even the simplest one, is how does this thing work? The idea of any thermometer would have to be some kind of device because it measures its temperature. If the molecules go a little faster, something needs to change in order for the thermometer to work. If the molecules go slower, that needs to be indicated with something that's changed. This one's pretty simple. What happens when these molecules go fast? Yeah, they bump around, they hit a little harder, they are going to move up the column. And so we call this a mercury thermometer. It can record whether this one and this one are in thermal equilibrium or one has more motion than the other. Okay. It's not the only type of thermometer. Not too much different would be this thermometer. This is an alcohol thermometer. Basically, it's the same idea, but instead of putting mercury down here, we put alcohol. But again, you put it in something, and if it makes these alcohol molecules move a little bit faster, they're going to go up the column. And so those are probably the most common type. How about this one? Maybe not quite as common. How does these little ones that are kind of on a dial work? Kind of a rounded object. Yeah, if we take this apart inside, and actually here's a really good one, but it might be a little hard for you to see, so let me grab here's a big one. But this one here, I don't know if you can see from your distance, this is the thermometer, if you will, on an old thermostat, but there's a metal wrapped up in a coil. Here's kind of a big one like that. Okay. And then, of course, what would happen when it heats up? Yeah, the molecule is going to expand a little bit. They're going to, uncoil, if you will. And these are liquid, so they go up. These are solid, so they kind of uncoil. But as they uncoil, then where the pointer is sticking up will change. And so the dial moves. But again, they're a thermometer. They do measure temperature. There is something about them that changes when the molecules change. A fun one, maybe two fun ones that are a little different from kind of the standard, actually maybe three here. I meant to bring my bigger digital thermometer, but all right, well, I'll bring a couple here. But this one here, this is what I would call a thermometer. It's a little different though. This is actually a pressure gauge up here. But I have some air molecules in here. And I've got hot water in here. And there's something that changes. We refer to these as air thermometers. You'll actually do a fun little lab on this. But what happens if I put it in the hot water? Something changes. In this case, it's the pressure. And so the pressure went up. It started at 15 psi. It looks like it went up to about 17 psi. On this side, I have cold water. So again, probably not a surprise. What do you think will happen here? Yeah, these molecules will slow down. They will not be hitting the bottom of this pressure gauge as hard, and the spring inside will respond to that and then move the dial down. And so this is kind of a spring-loaded diaphragm here based on these molecules going up the tube and hitting them, and that's based upon their motion, which is based upon their temperature. Exactly. This one may be a little more common in today's world, a digital one here. But in this case, and that's why I should have brought the big one out. Bummer. You'll see the big one later on here. But our bigger one has two wires. We'll use it in lab. But again, as I put it in something hot or something cold, the molecules are going to go faster and slower. Electrons are connected to those molecules. molecules. And so we can make the electrons go faster or slower. And if we have two pieces of metal, the difference in those two pieces of metal then can produce a small voltage, because the electrons in one of the metal are moving, although at the same speed as the other metal. They are different metals and they have different motions with them. And a small voltage is going to be produced, and then I can measure that small voltage. And so those are a lot of the common thermometers you see today. This one is one of my favorites. This one, the molecules kind of change their alignment. Here in this room, the molecules are aligned in such a way that they pretty much absorb all the light and they look black. If I warm them up, they will move and twist. Yeah, and you can kind of see just under my thumb there that they twist a little bit and they go to kind of a greenish color. If they twist even more, they'll go to a blue color. This one you can barely see. It's designed to not change until it warms up to 35. This one is already green. This one is designed so the molecules will already start twisting when it gets as low as 20. And so this room is already above 20. So they stop being black and they've already gone green. They will keep going at higher ones. So this is a good one to do in the room, because the rooms are usually about 22, 23 degrees. And so if I put my fingers on it or breathe on it, I can get it above the 25 and it turns blue. If I put a little ice on it, I can hopefully get it under 20 degrees. And it will turn black. And so again, it's a thermometer. Anything that changes, this will be fun to watch change back when it dries. Anything that kind of changes something that we can record. Where's the 20? What was? There's got to be a 25 to 30. I like the 25 to 30 because 25 is more than the room, so it's still black, but it only takes just a little bit. Well, that's my wet hand. Just a little bit, and we will get it over 25, and it'll change greens and blues right away here. And so there's our thermometers. Of course, not a surprise that we are going to use in our class and lab either a thermometer made out of some kind of liquid, so when we warm it or cool it, we see the liquid go up and down in the capillary tube, or some of our other equipment in lab is just simply digital. We take a wire, it's got two metal pieces on the end, we're going to shove it in the hot water or the cold water, and we're going to go, hey, what's the temperature? And it'll take a reading for us. It'll pick out the motion of those. And so we begin with, again, our thermodynamics with this idea of temperature. And temperature then scales. And so let's put some numbers in here. Let's kind of have a standard here. Now that we know this whole idea of what temperature is and how temperature is the average motion of these molecules, then we need a scale, if you will. I bet you're not surprised to hear that one of the first people to work on a temperature scale was a guy named Fahrenheit. So we have temperature scales. As you will quickly see, the Fahrenheit scale has its pros and cons. So Celsius will kind of step in here and do some adjustments. So we have a second temperature scale that we like to use, and obviously then they are doing the same thing, but they kind of define things and reference things a little bit different. And then after Celsius, Kelvin kind of steps in and says, hey, let's adjust that temperature scale. And there are other temperature scales, but simply put, let's take a moment to talk about the Fahrenheit scale, the Celsius scale, which I have a strong suspicion, again, you've already seen all this before you got here today, and the Kelvin scale, which I think you saw that too. That probably only was introduced to you in a science class, but I know most of you had me for 102, and I know we went through this same little pattern here of how do these scales work. Let's start with what Fahrenheit did here. Here is his clever design here. He, like all of these temperature scales I was trying to point out, needed something that changed. And so, thinking about how he could record a change in temperature, and at his point, not knowing that they were motion of these molecules, he did know that things did get bigger. And so watch what happens to this piece of brass that I have laid out across here. I'll show you this dial on this end. In fact, I'll move the dial straight up for just a second. But this piece of metal, if I were to move this rail back and forth, can you see the dial spin? And it spins a lot. And so this is purposely designed so it can pick up small motion. I mean, just a small movement here will spin that dial quite a bit. And so if I set it so that the dial is straight up and then heat it, what will happen? And Fahrenheit knew it would get bigger, but how much it gets bigger is proportional to its temperature. We know a little bit more than that. We know that these molecules are moving faster on the microscopic level. And as these molecules move faster, they're going to hit each other a little bit harder and they need more space. So yes, they will get bigger. So again, microscopic level, I think, is a little better way to see this, that they're hitting each other a little bit harder, they need more space. And I think you can see the dial, it moved about a quarter of a turn, right? And I'll leave it alone here, because as we sit here for the next hour, we will watch, well, it won't take that long, but I'll leave it here, and it will cool down, and the molecules are going to slow down, and this dial will move back. And so Fahrenheit realized that this little dial, a little expanding rod, would be a good approach to building a temperature scale. Now, I've kind of drawn it up here as a thermometer that goes straight up and down because I think that's what you're more used to, but Fahrenheit said, let's build a thermometer with this rod. We'll put a little dial on here, and now we just have to make some standard marks. And in his case, he picked the boiling water and the ice water. They're good, useful, easy to repeat situations. He took 2 buckets of water. One is a bucket filled with ice, kind of like this, which was fairly easy to get. You just go out and get some snow. Well, maybe not in Santa Barbara, but winter time, and get some snow and put it in a bucket. It's easy to get boiling water. You take that same water and you build a fire and put it. But if you run ice water through here and set the dial straight up, then change it to boiling water and run boiling water through here, the dial will increase. And if you adjust it so the dial goes a half circle, what do you call a half a circle? 180 degrees. So, sure enough, he labels his temperature scale as a half circle, 180 degrees. Now, it's too bad he didn't call that 0 and 180, as you might have guessed. He tried something else. Yes?
I thought Celsius was the boiling water and Fahrenheit was like a warm armpit.
Well, No, the lower one is the ice water. The boiling water is also a reference. Fahrenheit, kind of before he put all his thoughts together, did all kinds of crazy things. He did measure temperatures of the human body. He measured them sometimes when they were in good health and sometimes when they had a cold or a flu, so they got a little bit higher. There was a lot of things. And he wasn't a real good record keeper, so we have a hard time completely knowing what he did. But putting what little written information down that he did together with the most logical approach, this is kind of what he formulated after just doing all kinds of random things. So he didn't just sit down 5-minute period like we're doing now and say, here's my temperature scale. It's logically sound. It kind of developed, like most things, with time. But ignoring the armpits and the fever, these were definitely two spots he liked a lot, were the ice water and the boiling water. So no, it wasn't just Celsius who did ice water and boiling water. Fahrenheit did plenty of that too. He just did other things. In fact, the other one that is important in this discussion that he did was, how do you get something colder than ice water? Especially if you don't have a refrigerator. Yeah, add salt to it, right? And so he took this next step and took his snow and his water and he mixed it with salt, and that's what you chemistry people would call an endothermic reaction, right? It breaks it apart, gets it really, really cold. And then he watched the needle. And he watched the needle, and this time the needle moved the other way. I don't want to touch it because it is cooling down. You're seeing it's getting back down to the straight up and down again. But if I were to cool it down beyond that, then it would go the other way. And so when Fahrenheit did that, he noticed that it went back a little bit. And I don't know if you want to call this ice and salt mixed together. But that's essentially what he got. And he measured that angle, and he noticed it was 32 degrees backwards on the little scale. Which then explains his numbering system when he finally finishes all of this. I guess because this is the coldest he could get anything, he calls it 0. Which then makes this 32. Which then if you add 180 to 32, you get 212. And degrees. And so to this day, we call temperature in degrees, which is a little annoying because we're never quite sure when somebody says degrees, are you talking about an angle? Or are you talking about the temperature? And of course now you can see where he used it, because he really used it as an angle. He built a dial and didn't really want it to make it degrees, but he does. So what that is trying to say here, if you don't already know, is on the Fahrenheit scale, ice water is 32 degrees Fahrenheit. And boiling water is 212 degrees. I just love that word, degrees. Fahrenheit there, right? Just really throws people off there. All right, so that is our Fahrenheit scale. Continuing on with this discussion, and kind of fitting in with the decimal system, the metric system, base 10, Celsius says, let me kind of improve this a little bit by doing the following. First of all, ice water, boiling water, good reference points. Nobody really works with a whole mixture of different salts and ice and water. Not a real good reference point. So his first decision is to change the 0 from this mixture of salt and ice to ice water. Much more common, much more of a discussion, and so that is 0. And not using a dial that is a half a circle, which is 180 degrees, but using a base 10, let's chop ice water to boiling water in some kind of base 10. either 10 divisions or 100 divisions or 1,000 divisions or 10,000. And obviously, you know, he did decide to chop it into 100. I can only guess that he felt 10 was not enough. That would make it too big of divisions. And 1,000 would be too many. And so he settles on 100 there. And so you know today then that the temperature of ice water on the Celsius scale is 0. I love this part though. 0 degrees. Yeah, you don't need the degrees, right? That was all this change, and he carries the degree. Again, I think by that time it just has stuck in people's mind that you measure temperature in degrees, just like you measure angles in degrees. And so we still have the idea of degrees. So we call it 0 degrees, we call it 100 degrees. And that's that whole idea. Well, Kelvin comes along. Yes?
Is that why they call educational units degrees?
Ooh.
Thanks, David.
I don't know. But it's a good question.
For the Celsius for him?
Pardon me, what?
What was the low point, the lowest for Celsius? Fahrenheit at 0. What's that for Celsius?
I'm not.
Fahrenheit at 0?
So Fahrenheit 0, he referenced as the coldest he could get something, but that doesn't mean things couldn't get colder. So things could go below 0. And in this winter, if you lived on that half of the United States, it's amazingly cold. I mean, there was 2 weeks ago, there was like 100 degrees difference between Santa Barbara and Wisconsin or Michigan. 100 degrees. And I thought it was cold here. It was like 55 degrees. And I was like, oh, it's getting cold. And they were like negative 45. It's like, oh my goodness. I can't even imagine what negative 45 is like. So 0 is just kind of a reference. And things can get colder then. And I hope that answers this question. So Celsius, realizing that, moves it up to this higher temperature and says, well, let's call that 0. We could certainly get lower than that, and we could certainly have ice water, and we certainly could have lower than that. Yeah. Which actually leads into Kelvin, because then Kelvin comes along and kind of does the same idea and says, let's change this scale a little bit. It too has its pros and cons. And what is a new way of looking at this? And Kelvin says, you know what, making references to ice water and boiling water is very useful because it's really easy to get and everybody can do it. People are kind of familiar with ice water and boiling water to some degree, so that's a good place to start. He also says it does make a lot of sense to put 100 divisions there. It's nice to have a base 10 division scale instead of the 180. But what really bothers Kelvin the most, and as you will see, it will be very helpful in our equations, is 0 is just kind of a random point. I mean, it's ice water. In that sense, it's not random. But the molecules are moving at that point. And he's kind of the first to put that together and realize, wait a minute, temperature is the movement of these molecules. So perhaps what we should have is a scale that the numbers on the scale are connected to the movement of the molecules. In fact, he was the first one to put those together and realize there is something what we're going to refer to now as absolute 0. Realizing if you cool something down, what happens to the motion of those molecules? They slow down. If you cool it again, what happens? They go slower and slower and slower, right? And if you make it colder and colder and slower, is there a limit to that? Yeah, what's the limit? They stop. And so it was Kelvin here who thought that a much more appropriate decision would to put 0 where the molecules stop. There is a point which we now call absolute zero. There is a point that they can't go any slower. And so you have a zero there, and everything else then is positive numbers, and everything else numerically is related to the motion. And the reason that can become useful is all the physics that takes place is related to the motion of the molecules. So as we develop mathematical equations, the physics is the motion of those molecules. It's the Kelvin scale that the temperature is related to the motion. And so our formulas will come out much easier if they're on the Kelvin scale, because the temperature is directly tied to their motion. And you'll see that. And that's the real big advantage of the Kelvin scale. The reading on the scale is directly related to the motion. That is the only scale where 0 means 0 motion. The other one, 0, does not mean 0 motion. In fact, many of you, I think, know that the 0 motion, right down here, is really cold. It is way, way down. But again, Kelvin, at first not knowing how far down that is, realized that there would be a stopping point. There would be an absolute zero. And he wanted to develop a scale there of calling 0 at that point. So now he needs to figure out where that is. And he does a great experiment. You guys are going to do it not next week. You'll do one more on waves next week, but the week after you'll repeat what he did in finding this absolute 0. I think many of you know it. What is the value where they come to stop on the Celsius scale anyways? Yeah, negative 273 degrees Celsius. So it is way, 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 way down there. Okay? So if you extend that logic and say, okay, I want to call that 0 down here where they stop, then what does that make for ice water? Yeah, you're going to make them the same size. You're going to make 100 divisions. So this is 273. So not only is it a big number, it is not an even number. And that's a little annoying about the Kelvin scale. So you'll see that half the time we use the Kelvin scale and half the time we use the Celsius scale. Usually when we're making measurements, and particularly in the lab, we'll measure things in the Celsius scale. And then when we go to do calculations, since the motion of the molecules is what is happening with the physics, we will do it on the Kelvin scale. So we're going to have to go back and forth. What would boiling water be then? 373. And the best part I like, it is 373 Kelvin. No degrees. He finally throws away, as you pointed out, Celsius should have. But he says, look, no, get rid of this degree thing. So there is 373 Kelvin, there is 273 Kelvin, there is 0 Kelvin. And I got to admit, it's difficult to say. You won't be surprised to hear me a number of times these next couple of weeks, and I'll say, yeah, the temperature is 300 degrees Kelvin. 300 Kelvin. And it's just, that degree just wants to come in there somehow.
Is it possible to cool things to negative 273?
No, we haven't got that far, but the third law of thermodynamics we will eventually get to, that says you can approach 0 Kelvin, you can never achieve it. So we can get closer and closer and closer and closer and closer and closer and closer. And so like a good calculus problem with limits, you never get there, you get closer and closer and closer. And I think some of the record temperatures are like 0.000, and I want to say something like 12 zeros. Well, nano would only be 9 zeros, I think.
They got a billionth.
A billionth of a Kelvin?
Yeah, that was a Nobel Prize.
Well, don't quote me on this, but I think it's even lower than that. I think they've gotten to 12 zeros, so more than a billionth. They've got to a trillionth of a degree. But I'm not really sure. But anyways, I don't know if that helps with your question, but that's going to be our third law of thermodynamics, that you can't actually get there. Although, depending on who you ask, I would call a trillionth of a degree 0. Right? So it's kind of this, and the same thing you do in your calculus class. You can never actually take the actual limit. You get closer and closer and closer and closer. So if you added 1/2 plus 1/4 plus 1/8 plus, do you ever get to 1?
Yes.
And you keep getting,
It's Pico.
it's pico? Okay, yeah. Oh, good. I'm glad we got the, yeah. I'm glad we got these smartphones here. We don't have to keep guessing. Yeah. All right. But that's our temperature scales. So, as I was pointing out, the connection then of going back between these scales is going to be very important. Because, like I said, there's going to be some good things about the Celsius scale that we will like. And most of our scales that we actually do in lab and make measurements from will be on the Celsius scale. It's kind of nice to work and say, hey, you know, the room temperature is about 22. 21, 22 degrees. That's a good number. A little warm in the room today. It's 25 degrees Celsius. But to say it's a little warm in the room, it's 300 Kelvin. It doesn't sit well so with people. 300 Kelvin, that doesn't sound just a little warm. That sounds a lot warm. Or a person comes on the news and says, okay, today's temperature is going to be 273 Kelvin. Does that mean sweater or shorts? I really don't know. So the Celsius scale, we again are going to use and continue to use a lot, but a lot of our equations will be set up on the Kelvin scale. So fortunately, there's a very simple connection. How do we go from one to another? Right, and since they have the same spacing, they're just shifted in their 0. Whatever you have on the Celsius scale, if you add 273, you are going to get the Kelvin. Or the other way around. If you're on the Kelvin, you subtract 273, and you're going to get it on. So that's probably the easy one. And watch this. What about a change in temperature? Because a lot of the formulas we will have are going to be talking about how much did it increase by. It started at 20 and warmed up to 25. Now, was that a change of 5 on the Celsius scale, or was that a change of 5 on the Kelvin scale? Doesn't matter, right? A change on the Kelvin scale is the same as a change on the Celsius scale. And so a lot of the formulas we have are only interested in change. And so there's really no issue about, okay, are you measuring it as a change on the Celsius, or are you measuring it as a change on the Kelvin? That doesn't matter. But some of our formulas do directly matter on the absolute temperature. And that's usually because it involves the absolute motion of the molecules. And so there's a good chance that that equation has to be on the Kelvin scale, not the Celsius. And you'll need to pay close attention to that. I'll do the harder one. We won't do this too much, but because in science classes we like to say in Celsius and Kelvin here, but wouldn't there be a mathematical connection then between the Fahrenheit scale and the Celsius scale? And so if I put over here temperature on the Fahrenheit scale, temperature on the Celsius scale, and say how are those two related together? In fact, maybe if I just kind of draw a line up here, let's just say that each of these thermometers were put into, say, warm water, where the mercury goes up to here. I mean, the physics is still the same, whatever scale you use. The mercury goes up the same. It's just a matter of what reading do you have here compared to the reading here. Well, let's start and just ask, how many divisions are we above ice water? Well, that's what we meant here by the Celsius scale, right? The Celsius scale, if this if this said 20, what you mean is you're 20 divisions above ice water. So how many divisions would that be on the Fahrenheit scale? Would it still be 20? No. Would it be more or less divisions? There would be more little tick marks, right? You're trying to fit 180 little tick marks in here and only 100 here. These are closer together. There's going to be more tick marks. How many more tick marks are here compared to here? Yeah, there's 80 more, or a ratio of 180 for every 100, right? So that means whatever number I have here, like say a 20, 180 over 100 would tell me how many tick marks I have on the Fahrenheit scale. Right? I would have that many more. Of course, the other thing I need to be careful about, that's just how many above ice water. But on the Fahrenheit scale, this above ice water is already 32. So the last piece of this needs to add 32. And I suspect most of you are familiar with the reduced fraction of 9/5 times the temperature on the Celsius plus 32. And so that is the mathematical connection between the three scales. Fahrenheit to Celsius, and then Celsius to Kelvin. And like I said, we won't do too much then on the Fahrenheit scale, but it's around us and we're going to want to live with it. And you might want to ask yourself many times when we have a problem and it says, 50 degrees Celsius, I think most of us are probably a little more familiar with, well, where's that on the Fahrenheit scale? Is that, how hot really is that? If the weather forecast said 30 degrees Celsius, most of us might still be asking, okay, 30 degrees Celsius, what do I do? What do I wear here? Is this shorts or pants? No, right? But we can convert it here into the Fahrenheit scale. Well, again, let's keep going here. This whole illustration of temperature scales led quickly then to thermal expansion. I didn't really use the fancy word thermal expansion. Maybe I should. In fact, I'm going to pull down the overhead here and show you a couple of pictures with thermal expansion. So maybe I should clear the board over here so I can give myself some room to write. But indirectly, I have been doing thermal expansion because right away, and about an hour ago, I said, well, when you warm them up, the molecules move faster. If they move faster, they need more space. And so, even though I was talking about temperature scales, I already showed you thermal expansion, didn't I? I mean, maybe we should review. Why then did the higher temperatures get recorded up here and the lower temperatures get recorded down there? Thermal expansion, exactly. You put this in something hot, these molecules are going to go fast, they're going to hit a little harder, they're going to need more space, they're going to go up. If they slow down, they're going to go down. Every thermometer built like this, you will discover the low numbers are down here, the high numbers are here. Doesn't help to turn it over. Same thing, high numbers are here, low numbers are here. It is the size of the material, which in this case is mercury. And the other one I showed you was an alcohol. And the other one I showed you was just a piece of brass. Maybe I should show you some other ones while we're here. Some of you will remember this from 102, but if I take a little bit of gas and light it and make a hot flame, take this metal sphere, it is designed or manufactured to just barely fit in that ring right there. So what will happen if I heat it? Yeah, and that's this whole idea of the thermal expansion. There is a transfer of energy right now. There's heat, right? Energy goes from the flame into this brass sphere. And as these molecules go faster and faster and faster, they need a little bit more space. Now, it's not so much that you'll be able to see it with your eyes. Is that bigger? But it won't fit. If I cool it down, oh, that would work too. It will fit. And so the size of our metals, our liquids, our gases are all going to be connected to this question about, well, what temperature are they at? Because there is a thermal expansion. And that's going to play sometimes a useful role, sometimes an annoying role. But either way, we have to design and manufacture around it and take it into consideration. And it's been a while since I mentioned it, so I'll say it again. It's this kind of what I'll call cleverness that leads to new products and better products and success in the business world, because you go, okay, what could I do with this? You know, what if things do get better? What can I build? And who knows, you may discover something that hasn't been done before. Sell thousands of objects, make millions of dollars, and then not forget that our school is in desperate need. You got your start here. We do take donations, and I like my Ferraris red. Right? And so that's what you will be looking for. What could you do when things get bigger and smaller, when they get warm, or other properties? So again, it doesn't fit. But here's a tough question. What if I warm the ring? I'll leave the sphere in here so it stays warm. But I guess what I'm really asking you is, now that I have a ring with a hole in it, and I heat it up, does the hole get bigger or smaller? I'm not quite there yet. But I think this one can be a little surprising. The hole, not there yet. The hole actually gets bigger. And it is an unfortunate first three, there we go. But the hole does get bigger. To convince you, I shall cool it down. And the hole gets smaller. And so the size does change. And in this case, the hole gets bigger when you warm it up, not smaller. I made a mess up here. And before it runs all over the place on somebody's homework, too late. Well, I'll try to block it, at least for a little bit. Get some more papers down here. Kind of deal with that. All right. But let's take a closer look at that. And I think your author did a good job in the picture here, so that's why I wanted to turn on the computer. Yeah?
Why do microchips still work if they like heat up and expand? Like,
well, microchips, and this is the, I would call the bad part of thermodynamics, is everything now is going to get a little bit bigger. And I should say thermal expansion. Computer chips are exactly that. They will get bigger. But they are designed to get bigger and still operate up to a point. If they get too hot, they break. It gets bigger and bigger and bigger, and eventually they crack. And so you have an operational temperature where they will work. But you have to design for that. And that changing in the size is really an unfortunate limitation of the
That's why you can only get
world.
so small.
Yeah. Yes. And other reasons, but yes. And I'm trying to see where your author, he's got a picture of the ring. This is not it. This is him actually doing it. Is it a homework question up here? I don't even seem to have all the pictures.
Well, I know there is a homework question.
Yeah, and I think that's the one I'm thinking of. Well, I'll just draw a picture here, but I apparently don't have it there in my library. But here is the idea that if you have a ring and it is, you know, a certain size, and you warm it up, be careful on your logic. It's really easy to only do half the problem here and say, hey, let's look at that molecule. That molecule is going to move faster. And it's easy to say it moves faster in and out of the circle. But that's not all it's doing. What else is it doing? Around the circumference. It might be actually a little easier to see, in my view, if we had a square hole. I know we don't, so we'll come back to the circle. But when I have a square hole, again, it's very tempting to look at just the left and right motion of that molecule. And if that's all you look at, you think, oh, this is going to move in. But remember, there's this up and down motion. And that changes the length of that side of the square. And it's the length of this side of the square that determines the size of the opening. And so if this thing were to warm up, and I'll exaggerate, because I do want you to see that the hole does get bigger. Yes, this does get wider. But it doesn't get wider in the sense that it moves into the hole. What happens then is all of these expand outward, because that's what's happening with all of these that are making up the size of the hole. And so, interesting enough, the size of the hole does get bigger, and maybe not a surprise that the size of the hole gets bigger by the same amount as if there was metal there. And so keep that in mind when you do the homework, and that would not be this weekend. This weekend you're studying for the test, but the next weekend, that if you go to calculate how much bigger does the hole get, you can treat it as if, I know there's not really material there, but you can treat it as if there is material there. Because remember, why is this getting bigger? Because that material right there got bigger. And that's why you can calculate the size of the hole getting bigger in exactly the same way as if there was material there. And of course, I kind of showed it with a square one, but hopefully you would see by extension of that, this circumference would get bigger. And so again, an exaggerated picture might look like that, where the opening in the hole actually did get bigger because the circumference got bigger and the width actually got bigger too. And so this did get bigger. I'm not saying that this got smaller. I am saying the width got bigger, but the opening got bigger also. And it got bigger as if there was material there, because it is that material right here that defines the size of the hole. So it's going to make our problems actually with holes in it pretty easy to calculate. And I wanted to make sure you caught that, because that's always a homework problem on this first chapter that throws students off. They go, okay, the first problem said, how much bigger did the rod get? No problem, I calculated that. But then the next one says, you have a piece of aluminum, you drilled a hole in it, and you heated it up, how much bigger did the hole get? And they're like, how do I calculate the hole? And so I'm trying to tell you that the hole is defined because of the material around the hole. So treat it as if it was filled with the material, and that would be our answer of how much bigger it gets. And in fact, your author shows you some challenging design features with thermal expansion. And like I said, there's good and bad in thermal expansion here, and the clever engineer and scientist takes advantage of those and engineers around the troubles of them. Think about a railroad track. This is one of my favorite pictures. It's a real picture. But if you had miles and miles and miles and miles of a metal rail, what happens on a hot day? It expands. And if granted, this 1 meter may not expand very much. You saw me warm this up and it did not expand that much. But if every meter expanded a millimeter, once I get 1,000 meters, a kilometer, that's going to expand a whole meter. Is that a lot or what? Yeah. And so a kilometer worth of track can expand a whole meter further. And so how do you design for something like this? When you're, yeah, you put expansion joints in there. If you've ever looked at a rail system, they put in a rail. They don't put in a whole kilometer of rail. They put in a rail that is, well, varies, but I'll call it 20 feet. Then they put a second one and they put a little gap in it. What's that gap for? Because there's a hot day going to come along. And that hot day, that's going to come together. And the other rail is going to come together. And the other rail is going to come together. And by the time you have a whole kilometer of these laid out, there is an open gap the equivalent of 1 meter. And there's room for these things to expand. This picture is great because these rails, somebody forgot they were supposed to put a gap between them. So they put a rail down, and then another rail, and then another rail, and then another rail, and then it got hot. Well, what's going to happen? It's going to grow, and it's going to need that space. And that space, in this case, came out in a twist.
So you didn't even have an okay job after that.
Right. So, yeah, it's not even a C student here, right? This one just missed the boat altogether. Yeah. Our campus here, you hear it well because the train is right there. And on cold mornings, you'll hear the train really loud. Click, 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 click. The gap is huge if you go down there and look at it. And on warm summer days, it closes up. And not all the way. You still want to design for that rare consequence that it's extremely hot. But it closes up and you don't hear the train with the same intensity. It's just barely going over the rails. The gap is much, much, much smaller. And that's what they're trying to show you. Bridges are another big challenge. I think your author has a good picture of a bridge in here too. If you look at one end of a bridge, there is often these kind of teeth like this, so that on cold days it'll pull apart, hot days it will move in. Either way, hopefully there's never opening where something or someone or some car can fall in the middle, but it's designed that cars can still go over it, but it's also designed so the bridge doesn't end up like that rail did. And so the expansion of those are critical here in the design. And as this is the picture I was looking for. Yeah, all right, little Bunsen burner under there. But a useful design, and somebody taking advantage of this instead of engineering around the consequences of it, is what if I did something like this? Now, one thing I need to add to this then is everything is going to get bigger as you heat it up, but will different materials expand the same amount? Yeah, and as we'll see in a second, we haven't got to any numbers yet, but if I were to build something, and in this case what's called a bimetal strip, so that I've got two different metals here, And so maybe this right here is the cooler temperature, 25 degrees, and this is the warmer temperature, 30 degrees. And I put these two pieces of metal together, we are making a contact right here. And maybe that's electricity. And so electricity flows from here to here, and then, you know, on to wherever. But there's actual physical contact being made here. Good example is this thermostat. Right now, there is a contact, but at that point up there, and the electricity can flow through here. And in the case of a thermostat, that electricity would turn on the furnace. And so at this particular temperature, contact is made, the furnace goes on. This is the cold temperature. What happens when it warms up? There's an expansion, right? And as these thing expands, it pulls away and breaks the contact. And then in this case, breaking the contact would mean it would pull away here, and this would turn off the furnace. We no longer have electricity flowing through. And if I warm this up, I think you'll see it pull back. I can warm it up. Again, this is the biggest one I have, but can you see it is touching? Right there, it's touching. And if I put it over the flame without burning myself, do you see it pull back? Pulled back a lot now, right? And so as it gets warmer and warmer, it pulls back. As I get it out of the flame, it's going to cool down. And as it cools down, it will get closer, 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 and eventually we'll get it back down and it will make contact. So using the thermal expansion, in this case to turn on and off a furnace. This one you might recognize as an ironing. It too has a little bimetal strip down in here, and so I can set the dial, say, on medium. And what happens is the electricity will flow through for a while, warming it up to some point, and then it'll break contact and the electricity goes off. I mean, don't get me wrong, it's still plugged in. I still have the switch on, but the electricity does not flow anymore because the bimetal strip has made a disconnect. And then maybe a few moments later, it has cooled down enough that the bimetal strip makes contact. And so the electricity goes on, off, according to its temperature. There's nothing I need to do, but that keeps my iron at the medium heat, or whatever I set the dial for. Thermostat in your car, very similar to that, in the sense that this end would go down in your engine block. Here's the engine. When the car starts, the cooling water around your engine block is cold. And because of that, it blocks the flow of water. No water circulates while the engine is cold. When the water warms up, it will then pull this back and let water, and now the water can flow through. It can go into the radiator in the front of my car. The wind can blow through my radiator, cooling the water as it goes back. And so now I circulate the water. So when the water's cold, no circulation, because that's what I want to do, is warm up the engine. I don't want the water to cool it. Later on, the engine gets warm, then I want the water to circulate it. And so the engineers have designed a very simple advantage of the thermal expansion. I even have a bimetal strip up here to illustrate it. It's hard to tell. It's bimetal. It's been burnt so badly over the years. But this side, you can still make out it's stainless steel down here, and the other side is brass. And brass happens to expand a little bit more. So as I put this piece of metal in the flame, you will hopefully see it curve. This side is brass, this side is the stainless steel. And so as the brass got bigger, it forced kind of an arch over the side, because the outside is a longer length than the inside. Now I think you're seeing it cool down. And as it cools down, they're getting back to the same length. So they were designed two pieces of metal the same length at room temperature. They welded them together and then say, well, when you heat them up, they're not going to be the same length anymore. So they won't be the same shape and they will curve around. And how much curve they have is going to be a function of their temperature. It could be a thermometer for that matter. Or it could just simply make connections or non-connections. Did I see a question? Yeah, David.
How do they do it? Because heating them up to weld them is going to make them a different length. How do they
Oh, in the manufacturing?
Yeah.
There's not just a single answer to that. What if, I'll just do a spot weld. I could take two tips of electricity and I quickly pass electricity just through that point. So I don't heat up the whole thing. It's a small piece of that. And there's other vacuum welds that work. Glues even work, but I think this is more than glue because I get it pretty hot. Yeah, yeah. Let me keep going with this because here is, I think, my favorite picture of all when it comes to thermal expansion. This plane. For those of you who might recognize it, it's the SR-71. Like any plane, it flies through the air, there's rubbing, and it gets hot. So as the plane gets hot, what's going to happen? It's going to expand. So whether this is a car, whether this is a building, whereas it's a plane, the engineers need to realize it's going to get bigger and they've got to design for that. This one in particular, though, goes faster than Mach 3. It gets extremely hot and therefore it expands quite a bit. How do you deal with that? And in fact, this plane is, I want to say 108 feet on the tarmac and 109 feet when it's in flight. Okay, it's a whole foot longer. So when you build the plane with metal pieces, do you cut it so that the plane is 109 feet? Or do you cut it so the plane is 108 feet? How do you put the metal pieces together? All right, like the rail train, maybe we'll put little joints in here. All right, so what we could do is we could take metal, lay it out, right? Lay it out so that it's 109 feet with little gaps. The gaps are equivalent to 1 foot, so when it heats up, they will fill in, right? Fair enough, and that's exactly what they did. It's really kind of that simple. What about the gas tank? I should say fuel tank, I guess it's not gas. Yeah, so here you have a fuel tank with gaps in it. Uh-oh. That doesn't sound so good. And most planes we could do different materials. Not this one. It's too fast. It can only handle titanium. Anything else ruins. Can't put a rubber bladder in. We can't make it out of metal. Too heavy. What do? Just let it leak. I love the design here. Instead of trying to design around it, they redesign the fuel so that it doesn't explode on you. And so what you do is you go out and you fill up the tanks and you just let it leak. With the idea that hopefully you will take off real soon. You will get going real fast, real soon, and you will come together. And that's why this picture is neat, because many people don't recognize those black strips. What are those? That's fuel leaking. That is jet fuel leaking out of the plane. This plane was obviously full down in the tarmac. It is now taken off, and it has started to warm up. If it was completely warm, you probably wouldn't be able to take a picture of it. It would be going way too fast here. So it's kind of in the intermittent ground. I would suspect that this is actually a fuel tanker right above it, because they're about to lower down and fill it up. That's the fuel tank right there. And so they're going to lower down a boom and fill it up with fuel, because even though you fill it up for it to take off, it doesn't have any fuel in it. It used some of it for takeoff and it leaked out the rest of it. So if it's going to go on a mission, you got to fill it up again. And so you fill it up in mid-flight there and then take off here. And so it's, like I said, really interesting design and dealing with, in a very simple way, an extreme condition. And they just did it with fuel.
Like sponge in between or something?
Well, because this thing is going to be operating at near 1,000 degrees Celsius. You put anything spongy, it just burns up. Yeah. So we can't make it. I think, and I think that's why it's titanium. I think even the aluminum would be near melting and be weak, and you couldn't make the same plane that fast out of the aluminum. All right, here's a clever design. It's too bad the picture's kind of foggy here, but here is a good usefulness and somebody working around the cleverness here of thermal expansion and saying, well, things are going to get bigger and smaller. What could we do with this? Now, maybe this is old school here, but you could take something like, in this case, a bunch of wood, kind of fit them together. You don't have to glue them or put any nails. How do you hold them together? Well, you have a metal band around it. But this metal band is first put in the fire. You get it really hot as you can get it. When you take it out, it just barely fits over that wheel. And so if you could imagine this warmed up, and I slide it just over the top of something, and now I let it cool, what happens? Yeah, it tightens up, makes a nice tight grip. There's no screws or bolts or glue or weld needed. It just is sitting there with, you might call, friction, a tight bond here on it. And although this is an old school one, it is still very common to use. In fact, there's a local company that does this for the Abram tanks. They design the axles of the tank, and what they do is, as they put the drive on it, they got the axles, and they take these pieces, and they do both extremes. They take the axle and cool it down in a dry ice bath, and then they take the outer part and heat it up. So they make the hole a little bit bigger, they make the shaft a little bit smaller, they slide it into place, they put it where they want, and then leave it alone for a few hours.
And then slip out.
Well, it would have to get extremely hot and extremely cold. Yeah, so you're going to have to test this and see how well it works. And you guys are too young to probably remember the first Gulf War, but that was their first true test. Their first true test was Gulf War I. When was that? 91. But I remember some of the local workers around here that were just ecstatic. They're like, yes, no axle broke. It performed outstandingly, and all the things that they had tested and predicted for all came to fruition. Didn't have any troubles. Because there is that question, once you get into battle, are conditions going to be more extreme than what we test? And but they do some pretty severe tests. I remember working in McDonnell Douglas. We had this great chamber. It was down here, was something like minus 70 Celsius, and up here was 90 degrees Celsius. And to me, the only way I could kind of describe it is this was kind of like a refrigerator door, a freezer door, and this was kind of like an oven door, and then, you know, they were partitioned with a trap door, because my job was to take the electronics that we had built and make sure it was all running. And so I used to like focus on the mountains and get a good picture, and okay, there's my picture. And then I had to take that and put it into the freezer, close the door. And I had to monitor the electronics and see if anything went wrong. And then push this little button and the trap door opened and it went right into this oven. And that electronics had to be perfect. It was going to go on one of the Apache helicopters, and it had to go from extreme cold to extreme hot. And some of the other electronics were going on the F-18. And I remember even talking to him, I said, isn't this a little extreme? Or, you know, are we overkill? And he goes, well, we are testing it because conditions can get extreme. But if you can imagine an F-18 on the deck of an aircraft carrier, it's sitting in the jet wash from the one in front of it. So the electronics are going to be extremely hot. And then 30 seconds later, it is now at 50,000 feet and extremely cold. So the change in temperature, obviously you don't want the plane to crash because of the fouled up electronics. And so these tests are there. Here's another one, and we better move on to our numbers. Oh, and we are down to 10 minutes, right? All right. So That's a little later. That won't be today. Well, I guess these are kind of the same thing. Here's a pipeline. This happens to be the Alaskan pipeline. And so you take this pipeline, hundreds and hundreds of miles. What happens between hot and cold days? Summer and winter. What happens to that pipeline? Yeah, it's going to change its length here. And this one is purposely designed. See that kind of S shape as it goes through the forest? Why not go straight? Well, if you went straight, what happens when it cools down?
It bends anyway.
Right? Well, when it gets hot, it bends. What happens when it gets cold? It gets under tension and it pulls apart. So the easiest design is to make it already bent. Because now what happens on a hot day? It just bends a little bit more. Cold day? Straightens out a little bit. And if you look closely, I don't know if you can see them, but there's 3 feet of movement on each side that this pipeline can shift around on. And so this pipeline just kind of shifts along. And when this pipeline goes on to the different servicing stations or the collecting areas, they do this with the pipes. And again, when it gets cold, what's going to happen is this is going to go like that as this thing stretches many, many meters to make up for those hundreds of miles of pipe that are shrinking. And then on hot days, they're going to come together and make the bow a little bit bigger. And so again, very, very clever dealing with this challenging problem of expansion and using it for useful things as well as designing to get what you want and having to make sure it doesn't break because of it. Well, before we do closure today, let's put some numbers in this. Because at this point, I've just been spending the last minutes here talking about the concept of the thermal expansion and kind of designing using it as a design or designing around it and dealing with the thermal expansion. But there's some numbers that should come in to play here. And so let me put some symbols. I'll put L for length. And so maybe if we go back to where we started over here and say, okay, look, this is the length of, say, that brass rod up there. All right? Then, as I heat it up, it's going to change its temperature. So, delta T, let me call that change in temperature. Okay, hopefully those are pretty obvious symbols. Let me put a delta L for representing then the change in the length. And so this thing is going to get a little bit bigger. And it probably doesn't surprise you that the change in length, delta L, would somehow be related to the delta T, right? If you heat it up 1 degree, it's going to expand a little bit. 2 degrees, probably twice as much. And we would say in a math class then that they are proportional. And so I'll put a little symbol up here, alpha. Are you familiar with that symbol for proportional? So I do want to pause and point out that we are also going to use that symbol for something else. So you're going to see alpha twice. Of course, we do that to make sure we confuse students. The more we confuse students, the more they drop out, the higher salaries go for those of us that succeed. And it's a real simple process. All right? All right. But I do want to warn you about the alpha. Because in this step, I mean the proportional statement. Okay? And so it should be proportional. But let me ask you this. Wouldn't the amount of change also be proportional to how long it is? I mean, what I'm trying to say is, if I had 1 meter up here and I heated it up so that 1 meter expanded 1 millimeter, what do you think would happen if I had 2 millimeters up? I mean, 2 meters instead? Well, each meter would expand 1 millimeter. The total expansion then would be 2 millimeters. And that's just a nice way of saying the expansion per meter is related to temperature change. So your total expansion depends on how much material you have. That's why you see most of these extreme examples I was showing you had either really long material like the rails or pipelines, or they were warmed up by an extreme amount like the SR-71. Okay? If you put those together mathematically, then you can go from a proportional statement to an equality statement by saying delta L over L is equal to delta T, where you need to put in this proportionality constant, right? That's how you change a proportional to an equality. And I'm only taking this kind of slow because guess what symbol we use? Alpha. So delta L is to L as alpha delta T. And so this is not the proportional symbol. That is my proportionality constant. And that can get a little confusing unless I think it's pointed out. And then once it's pointed out, I don't think it's hard to see. We will call it then the coefficient of linear expansion. We will probably write the equation more like this. Delta L equals alpha L delta T. That's where it'll probably be more useful to us. And that way you can see the three factors that determine how big something is going to expand. Right there, delta L. How much bigger is something going to expand? What does it depend on? Well, number one, how much are you going to warm it up? Makes sense. Number two, well, how long is it? Because each meter expands by the same amount. And then finally, number three is this is the material itself. This is the proportionality constant. This is the linear coefficient. This is how much does it expand. And so the last thing I'll show you here is your author gives you some of those numbers. You can go into the laboratory, you can measure all of these, you can see how much bigger it gets, and here is a table of those. The number we would use for aluminum, 24 times 10 to the minus 6. Notice they're all pretty small, meaning that if this number here is going to be noticeable at all, you've got to either warm it up a lot or have a lot of length. Otherwise, you're just going to get a small increase. Which, of course, if you put it on a dial like this, a small increase you can detect. And then you can see some of these. Like, for example, steel has a much smaller expansion than aluminum. Aluminum's more than twice that of steel. So if you have a piece of metal that under those conditions is made out of steel and grows 1 millimeter, aluminum would have grown 2 millimeters. And so that can be a challenge of designing things with aluminum. They get a lot bigger. In fact, many of you might have your aluminum blocks versus your old steel blocks. And that had always been a challenge, making a car out of an aluminum block because the aluminum expanded so much. But the trouble is when you start the car, you have these pistons inside that are going to change their size because they're made out of steel. And then you have an engine block made out of aluminum that is going to change twice as much. And so how do you deal with the different materials? And you want to get a tight seal when the engine is cold and when the engine is hot. Well, we'll call it quits for today and so there, but